Rabalnik. I am at Lithoz in Vienna, and I work here as a business developer in the medical department. And today I will tell you something about the LCM technology in general, as well as the dental and medical applications and our newest possibilities and the newest things that you can do with our technology. Let's start with a short overview. Lithoz is the world's market and innovation leader of 3D printing of ceramics. So from Lithoz you can get the whole solution for 3D printing. We offer the 3D printers as well as the materials, the software behind it. And it's also possible to let's do some material developments together if there's some material you want to print with and with this not from us or which is not in our product field, that we can develop it together. So it's really important for us that we have a good cooperation with our customers and that we are always there to develop everything together with them and help them if they need it. We are more than 70 employees right now. We have stay in 2 locations. One is the headquarters in Austria in Vienna, and the second one is in the USA in New York City. And we sold more than 70 machines worldwide until now. And 1/4 of our customers bought more than 1 machine from us. So that's the thing that we're very proud of, that that our customers are so happy to work with us together that they want to invest in more machines and in our systems. So this is in short overview of our reference customers. As you can see here, we have many customers from the industry, but this is just a few. There are just a few of it. For example, Kalis Martin or Cerix or Otto Baltic Implants, so many medical companies, as well as some competence centers for R&D institutes, so like the Technical University of Berlin, Fraunhofer IKTS, or the University of Zurich, for example. There are many cooperations we have with such centers like this. Now, just an overview, so go deeper in the LCM technology and how it works. LCM, the word, means lithography-based ceramic manufacturing, and I will show you how it works, how the process works. So this is a short overview from our process chain. As you can see, it starts everything within CAD design. So you have a file or a geometry you want to print, and you put it with our software on the building platform at your computer, and then you can print it up. And I will show you later and how to build the part up with our technologies. If the part is built up after the print run, you have to debind and sinter it. So you got to get a green body after the printing process, and afterwards you can debind it. So the part will debind and are then sintered, and then you have the final product. This is the principle of our technology, so how it works. With the principle of photopolymerization. So as you can see here, there is a 3D CAD model, and our software sliced this model into the images. And then we have here in our projection system, we have here a blue LED, and here is the projection system, and the blue LED shines at it, and there are mirrors that I can show you later. There are mirrors on it, and the mirrors project the layer you want to print on the bottom of our vat. So the material, the slurry is in the vat, and from the bottom there will be the blue light, and because of the blue light the material gets hard, but only there where the light comes. So you can see here the white one is the layer, and that's the area which gets hard, and that's the reason how you can print the ceramic and how it works to print it. You can see here how our projection system and our machine is built up. So I will start from the bottom here. You have here the LED, as I told you before, and this is the optical system. So there are many mirrors which project the layer you want to print. on the bottom of our vat. And this number 2 is our vat, and from the top of the machine, the building platform comes down and dips into the vat. Then the projection system projects the layer on the bottom of the vat, the material gets hard, and then the building platform comes up again. And that's the process how the part is built up. So you can print it then layer per layer. So the projection system projects every layer per layer on the vat, on the bottom of the vat, and the building platform dips down. The material gets hard and stays at the building platform. It comes up, and the next layer will be projected. So that's the thing, how it works. And now a bit deeper in the debinding and sinter process. So you can see here that we showed it with a geometry, and this geometry is actually our CEO. And you can see here that this is our green body. So this is the part, how it looks after it gets out of the printer. And you can see here in the graphic that you have, after the fabrication, you have the slurry, as I told you before, which is mixed from ceramic particles and photopolymers. The photopolymers are necessary that you can print a part and build it up with the blue light. So that's the reason why it works and how it works. And when you have these together, you can see that you need to debind it, that all the organic stuff and all the photopolymers are burned out. So you can see the part is a bit smaller after the debinding process. But it's also, you can also see that the yellow, there's many space between these yellow dots, so it's not that dense, the part. And that's the reason why you need the sintering process. So it gets sintered afterwards, and then you can see how big the shrinkage is between these parts. And then you have a full dense part only with ceramics, because the debinding process burns out the whole polymers and organics, and then you have only the ceramic left. And the shrinkage between the green body and the final result is between 25 and 30%. So there's a big shrinkage, but we know the shrinkage before, and that's the reason why we can print it and build it up, and the part is as big as we want it in the end. So here a short overview of our machines and printers. We started with the Serafab 7500, and last year in March, so 2019 March, we presented the Serafab 7500 Dental. In November 2019, we were at the Formnext fair and presented our newest system, so the Serafab S series. So this is the Serafab system series and the family of it. The difference between the machines is, between the older ones and the newer ones, is, for example, the speed, as well as how big you can print the layers. But the difference between the machines in general is most of the time the lateral resolution, as well as the number of pixels between these two types of machines, and the building volume. The building volume is a big difference, because the Serafab system S230 is, for example, the biggest one, and the Serafab system S25 the smallest one. Yes, so it depends on what you want to do. And you can see here that you can buy the new Serafab system machine in only one unit. So you have your machine with your docking station, where you can operate the whole machine and start the print runs and something like that. And it's also possible to buy more units. So you have module machines here, and all of these machines are controlled with this control station. So you have one point where we can start the print run for all 4 machines, and you can have one dock station where we can stop it for all of them. So this is really interesting for industrial standards and for the industry. And now a bit deeper in the ceramic materials in our portfolio, what we have. I just want to give you a short overview why ceramics in medical engineering, why it's important to have this and why we do it. Ceramic is bioinert and bioresorbable. So it's also possible to print with our printers bioresorbable materials, such as tricalcium phosphate or hydroxyapatite. The ceramics is non-allergic, so there are no irritations or something like that. And you have no artifacts at the CT or MRI. It's also easy to sterilize and has a really high mechanical strength and no electrical conductivity. This is just a picture from our material portfolio. So as you can see here, as I told you, this is tricalcium phosphate, for example. The blue one is the hydroxyapatite. These two are the bone replacement material. It's also possible to print bioglass as well as alumina and glass ceramics, for example, silicon nitride, as well as zirconia. It's also a lithium disilicate. Sorry, I just changed it. And silicon nitride, of course, is also possible, which is a bit really interesting for the dental field, but I will tell you later a bit more about it. So this is a short overview of the medical materials. As I told you, our lithobone materials, which are the bone replacement materials, as well as lithocon, which is zirconia, and lithonit, which is our silicon nitride. You can see here down there that we have also different tested the cytotoxicity, for example, or genotoxicity, and it depends on the material, of course, how strong and dense it is. So it's a bit different between them. It's also possible to print translucent and colored parts with our machines. So we also already printed 3 utericized, 4 utericized, and 5 utericized zirconia. So you can see here that there's a difference between the translucency, and it's also possible to add some colors during the print run. We also printed already the translucent alumina, which we are really proud of, because this is not an easy thing, but it works very well, and we are on developing this field of material engineering. And as I told you before, it's also possible to print lithium disilicate as glass ceramics. So glass ceramic is really important for dental restorations because of the highest aesthetics points. Because as you can see in the picture there on the right side, that the zirconia crown is much more darker than the lithium disilicate one. So there's a big difference on the aesthetic point of view, as well as here you can see that there on this disc you can read the Lithoz, the written Lithoz logo under there, but not on the zirconia one. It's also good because it has a good and high mechanical strength, as well as the that is biocompatible, and it's easy to colorize. So with this high translucency, it's just a future thing for dental restorations. So now just a few points about bone replacement materials. So as I told you, tricalcium phosphate, this is the scaffold you can see here, the white one, hydroxyapatite, which is the blue one, and the blue cylinder down there, as well as blends of TCP and HA and bioactive glass. This is also possible to print. So now I will tell you about medical applications we can print and solutions and success stories that we have. So it's possible to print really high resolutions with our printers. So you can see here a lattice cylinder made of alumina, and you have struts between 50 and 85 micrometers big, and openings between 100 and 120 micrometers big. So I think you can imagine now how small the part is big, but how small the struts and the openings are, and that it's not really easy to see it only with your eyes, because you just need an optical help or a microscope or something like that. But it's possible to do, which is really interesting also for the pharmaceutical point of view. Many pharmaceutical companies need some filters or something like that made of just a small lattice structure. Here are one of the best of both worlds. Here's one of our ideas that we had for the bone replacements. And you can see that there's a round there and zirconia cage, and inside there's a scaffold made of hydroxyapatite. And this idea is because bone is the second most frequently implanted issue in Europe after blood. And normally they use autologous bone for really big sized and critical sized bone defects to fix them, because you need the bone needs help or something between to grow in. And there are many bad bad things behind this autologic bone using, because there can be an infection, there can be some issues at the point where you take the bone and there on the place where you put the bone as a new one in. And that's the reason why we thought we can check that and change that. And that's the thing how we created this idea, because you can see there's the zirconia cage around it and you can give it in the jaw. So the zirconia cage gives the jaw the stability it needs when the bone can grow in without any issues or something like that. So inside you have the bone bioresorbable hydroxyapatite. So the bone grows in and the bioresorbable material goes away during the bone growth in. So after a few years, the bioresorbable material is away and you only have the zirconia cage left, which is a really important thing, because many people don't like to have big implants in their body which stay there. But the zirconia cage is here for the stability and to help the jaw to stay fixed. And now a short overview of our dental restoration. So it's possible to print crowns, bridges, or veneers, for example. We have the finest edges. So our edges are down to 70 micrometers small, so really small. And we have also the sharpest fissures. So they are really fine and specific, and which is a good thing, because you can print, I don't know, 20 of these fine specific crowns in one print run, and it's easier to produce than with the commercial techniques you use for this. You don't need to polish it afterwards. So if you have the print run is over, it's the surface is so good that it's not needed to polish it afterwards. And of course, it's possible to stain it afterwards or cement it as you like. So it's also, the post-processing is possible in the same way like after commercial production things. As I said before, you can also print dental implants made of different materials. So it depends on what you want to do with. It's possible with zirconia, of course, alumina and silicon nitride, which is really interesting because of its anti-infective properties that they have. But many people don't like the gray color. That's the reason why the people are looking for a new solution, because the titanium, for example, is also gray. And sometimes you can see it under in the jaw. And that's the reason why the whiter materials are a bit more popular, I would say. You have a great design freedom, so it's possible to design your implant patient specific or as whatever you want to design it. And it's also highly productive to print these parts, because they are so small that you can print nearly 50 or 60 in one print run. And it's also possible to print frets. So this is an M2 fret, for example, inside there. So and screw implant is with an inside fret. It's also no problem to produce with our technology. So here's just a short overview about our medical applications and success stories. So we have our medical Serofab systems in Europe, North and South America, as well as Australia. We have biocompatible materials, as I told you before. We have already customers who did CE certification for medical devices with class 3 with our materials, and with medical devices which are printed with our materials and with our printer, as well as FDA approved material devices in class 2A. There are already more than 10 surgeries performed in 2017. So we are already in the human body with our materials and with our implants that are printed. And of course, it's possible to print bioresorbable and permanent patient-specific implants, as well as other medical devices. So now the full digital workflow, how to get from your CAD design to your crown in the end. First of all, you need an intraoral scanner, for example, to scan the place what you want to fix, or where is the defect, what you want to, where the implant has to be. And as here's the process chain again, as I told you before, and you can see here down the pictures. So here's the scan, for example, from the crown. So here you want this crown to be changed, for example, or to exist there. Then you can print the crown. Afterwards, you remove the parts from the building platform, you clean it, and it gets debinded and sinter it. Then it gets stained if you want to stain it, and then you have the final product afterwards. We have also new things to say. So we already have a new machine on the market this year, which is the Multimaterial 3D printing machine. And the first question you will get is why multi-material printing? So you can combine different properties and different materials, and therefore the properties of the materials in one component. So for example, transparent and opaque, you can also print 3D colored gradients, as you can see in the picture on the left there. This is a white tower with made of alumina with red stripes on it made of alumina, for example. You can also print thermally removable support structures combined with normal ceramic parts, as well as porous and dense parts, bioresorbable and bioinert parts, hard and ductile, or heat conductive and heat isolating, for example. And you can see here down on the right side how the different things what you can print and from the different materials. So the gray and the yellow one, for example, are different materials, or here the dots and the yellow field, or the color gradients. This is also a thing which is possible. And yes, so the dots will show you the thermally removable structures. So the photopolymers will be away after the debinding and sinter process. Our new multi-material printer is called the Serafab Multi 2M30. You can, inside of the printer, you have two beds. You can effectively clean the material changes, and it's better to print with two materials in this way. And it's also a really interesting point that you don't need, with all our machines as well as in this one, not that much material to print with, so as little as necessary, because it's really important for us that our customers can develop their own materials, that our customers can develop new geometries, or in this case, how different materials work together. So you can put together the ceramic and ceramic, of course. You can put together ceramic and metal, as well as ceramic and photopolymers. These are some samples that we printed already with our newest multi-material machine. So you can see here the ring on the left side, which is made of alumina. So the white ring with a color gradient, as you can see here. In the middle, the plate with the Lithoz logo on it. This is also a printed part with our multi-material machine, and the letters are made of zirconia, and the whiter field around it is made of alumina, for example. We also have these yellow discs, so you can see that around you have two circles, and the outer circle is made of alumina, the higher one made of ZTA, so zirconia, tungsten, alumina, and the inner one is made of alumina again. So you can also make designs like this, for example. And of course, biomedical applications. So you can print also the whole cage that I showed you before in one print run. So the cage here around it is zirconia, and the lattice structure inside is made of hydroxyapatite, for example. And as you can see, the ring here is as fired, so that means it's sintered already. This field with the Lithoz logo on it is also as fired, as well as the ZTA and alumina part, and the green implant down there is a green body, so it was fresh out of the printer, I would say. So what is possible for the dental field with our multi-material machine. So we have a 3D color gradient. So you can see here on the picture that it's possible to print colors. So we got these fresh out of the sintering furnace. So we didn't stain it or something like that. You can see that there's a big stripe. So the gradient is from yellow to white here. And there you can see how the gradient works. So it goes white and will be a bit darker to the down there. We just wanted to show these big stripes in between because we just want to show the big difference between the colors here. The writer crown, you can see that there is just one gradient on the whole ground, and it's a bit darker on the more jaw side, and on the top of the crown, it's a bit more white one. Yeah, so thank you for your attention, and I hope you get a short overview of our work and what we can do. And yeah, I hope you liked it, and I'm open for your questions. Yeah, so thank you for your attention, and I hope you get a short overview.
Hi, hello. Thank you very much for your information you shared with us. It's very interesting and attractive information. We